Good morning, students. I am NP Singh, a teacher in physics at DAV CCL Public School GDD. I welcome you all in this class. The topic of our today class is electric potentials and expression for electric potential due to a point charge. So first of all, let us learn definitions of electric potentials. So electric potential at a point in the electric field of a charge is defined as the amount of work done in bringing unit positive charge from infinitive to the point without acceleration and against the force of electric field. That is, potential at a point A will be work done from infinity to the point A by Q naught. Here Q naught is a test charge. It is a charge of vanishingly a small amount. So first of all, we calculate the work done for bringing the test charge Q0, and if for the charge Q0 work done is infinity A, then for unit it will be equal to work done infinity to A by Q naught. Instead of bringing unit positive charge, first of all we bring the test charge Q naught, because it is a very small value charge and it does not influence the electric field of the source charge. So instead of bringing unit positive charge, first of all we calculate the work done in bringing a test charge of vanishingly a small amount. So let us calculate the suppose Q is the source charge, and due to this charge at a point A we have to deduce the expression for electric potential. Let it is at a distance RA from the source charge. For this we have to calculate the work done in bringing the test charge from infinity to the point A. But here we calculate the work done first of all from P to Q. Here force is variable, since electric field due to the source charge is inversely proportional to a square of the distance, so it varies from point to point, hence force will also vary. So first of all we calculate the work done for infinitesimally a small displacement through ds, and then by integration we calculate the work done from infinity to point A. Let r be the distance of the points P, so that the distance of the point Q will be equal to r minus dr. Here, as we know that electric field is the force acting on unit positive charge, so if a positive charge is kept here, it will experience force in this direction, so electric field is directed along this direction due to this source charge. Suppose it is BE, and if a test charge Q0 is kept here, it experiences force Q0E in the direction of electric field. Q0 is a test charge. Now, in order to bring the test charge from P to Q, we have to apply a force in this direction. So it will be represented by Q naught E. This is the force which has to be applied to bring the test charge from P to Q through infinitesimally a small displacement dl. So the work done will be equal to F dot dl. Here F is equal to Q0 dot dl, and we considered the force against the electric field, so we have to consider minus Q0E, as here it becomes equal to Q0E dl and cos 180 degree, because displacement is along this directions and E is along this direction, so angle between E and dl is 180 degree. It becomes equal to Q naught E dl, and cos 180 is minus 1. So it is equal to Q naught E dl. Now it can be written as Q naught E and dl is equal to minus dr. Since in the directions of dl r decreases, so here dl is considered as minus dr. Now substitute the value of E. It becomes equal to 1 by 4 pi epsilon naught Q by r square minus dr. This is the work, a small amount of the work done in moving the charge from P to Q. But according to definition, we have to calculate the total work done, and it is from infinity to the point A, which is at distance RA from the source charge. It becomes equal to minus 1 by 4 pi epsilon naught Q by r square into dr. It is equal to minus 1 by 4 pi epsilon naught Q integral of minus r square r power minus 2 dr. It is equal to minus 1 by 4 pi epsilon naught Q r power minus 2 plus 1 divided by minus 2 plus 1. It is equal to 1 by 4 pi epsilon naught Q, and limit is from infinity to R. So 1 by 4 pi epsilon naught Q, and this is equal to minus 1, which when multiplied by minus becomes equal to positive, and R to the power minus 1, which is equal to 1 by R, and limit is from infinity to R. It is equal to 1 by 4 pi epsilon naught Q, and here we have left Q0 charge, so it is also equal to Q naught, Q naught, Q naught, and it is equal to Q naught. Now it is equal to Q naught and 1 by RA minus 1 by infinity. So the total work done becomes equal to 1 by 4 pi epsilon naught Q naught divided by R. This is the work done in bringing the trace charge of magnitude Q0. But according to definitions, potential at A is work done from infinity to A by Q naught. So it becomes equal to 1 by 4 pi epsilon naught Q naught by RA and divided by RA divided by Q naught. So potential at the point A becomes equal to 1 by 4 pi epsilon naught Q by R. This is the expression for electric potential due to a point charge. In the similar way, you can deduce the expressions for potential difference between the 2 points. But here, when you are asked to calculate or derive the expression for electric potential, there is a slightly changing in the definitions and the limit of integration. In case of potential difference, the potential difference definition should be given like this. The potential difference between 2 points, suppose we considered point A and point B. The potential difference between 2 points A and B is defined as the amount of work done in moving a unit positive charge from one point to another without acceleration and against the force of electric field. So potential difference mathematically expressed as it. Here you can find the expression for the potential difference in the same way as we have deduced the expression for the electric potential.